gonna start recording. Okay, so recording is started. All right, so welcome to CISP 310. I am TAC, and I'll be your instructor for the rest of this semester, unless something happens. Let's hope that is not the case. I assume that you have read the syllabus. So do we have any questions about the syllabus? No. Did anyone try to upload it to any type of LLM and just have it summarized? No. You guys actually read it? Or did you just make assumptions like, okay, this is just like any other class. Okay, let me quiz you on this. Okay, people who have taken my classes, please try to refrain from answering these questions. Okay, if you want to pass this class with a C, what is the percentage at the end of the semester do you need in order to pass this class with a letter grade of C? It's in the syllabus. And you can even go back to the syllabus to read it again right now. All right, so that is a quick quiz to see whether people have read the syllabus. Because if you have read the syllabus, it'll be one of the things that you will remember because it is not usual. Okay, so now I think people who have taken one of my classes can disclose the answer. Yes, please. Yep, 37.5%. Okay, so that's 3/8. Okay, if you manage to get 3/8 of all the possible points, you pass this class with a letter grade of C. Okay, so I think that's a pretty good indicator that most people have not read the syllabus. But I'm going to operate under the assumption that you have read the syllabus and you understand it. Okay, so that's going to be my assumption. I don't want anyone to complain later on and go like, I didn't know that was a policy. Yes, I have talked about it in the syllabus, and I made the assumption that you have read the syllabus. Okay, is that okay? Does anyone think that is not fair? No. Okay. All right. Very good. So important. Okay, that is actually important. Read the syllabus. A few other things to get out of the way. If you go to the announcement, okay, and I think some people may not have visited this announcement because otherwise they would have read the syllabus. So in the announcement, this is the second post that I made for this class. So there's a prerequisite concept checklist. It is a quiz, okay, but it doesn't count for any points. So, if you want to self-assess to see whether you are ready for this class, and if not, what kind of topics you need to catch up with in CISP 360, I would recommend those people to just take that quiz, okay? It doesn't count to your grade at all, okay? You can completely flunk it out or, ace it. It doesn't matter either way. Here is section 3, a link to the reading material that I recommend people to read before class. Now, when I say recommended, I really mean it, okay? Which means people who do not follow the recommendation may encounter some additional challenges. All right, so that's kind of what it is. I was told that the video does not work, okay? So I'm gonna look into it and fix it. And also for all of my classes, not just for this one, I prepared a bunch of stuff, okay, that might be helpful to some people. You can definitely read this or you can not read it, okay? It is completely optional. There are some of these mentioned tools that you can use, like the concept mapping tool. That's a thing that I made, okay, just so that you can, if you want a graphical representation of how concepts relate to each other, that's a tool that can do it, okay? It's open sourced, completely free. It is basically just a Google sheet with some fancy scripting, okay? So it's kind of useful. I think it might be useful to some people. I am using Markdown for all my notes. So if you want to get your own private stash of my notes and you want to make some edits, okay, you want to comment on some of the stuff that I wrote, you can definitely do it. okay? It's OER, which means it is open educational resources. Okay, you can download everything that I use in this class, make your own special edition, and as long as you don't sell it as if you wrote the entire thing, I'm all cool with it. All right. Or if you say, I noticed that you have made a mistake here, I want to help you fix that mistake, please. Okay, it is using GitHub, which means you can submit a pull request, okay? And then I can go ahead and review your suggested change. If your suggested change is all good, I'll just click a button and your edit to my material will become permanent on the internet. Okay, so that's kind of cool in a way. For those of you who want to look into learning how to learn, okay, how to understand something that is complex, the second link, which is an example of how to understand something that is difficult and abstract, it might be useful, okay? It may not be useful, but it is a resource that is available to you. So anyway, this is just a bunch of stuff that I have written, okay, that might be helpful to some people, and it's not required, okay? This is not required reading. So I'm gonna get out of here and go back to the content of this class. All right. So what we'll do is, okay, I spoke too soon. I probably should stay on this page because it contains a link to the material that I would like you guys to have read before this class. Now, for people who believe, but this is the first class meeting, how can you possibly expect me to have read something before the first class? Well, the semester actually started last Saturday. Okay? Did you guys know that? All right, I see a lot of nods. Very good. Okay, so that's why I can kind of give you guys some reading assignment ahead of time, because otherwise, this kind of material can be a little bit tricky to understand. All right, so I'm just going to follow this link here. Okay, right click, open in a new tab. There we go. All right. So what we're going to do is we are going to start with transistor types. Okay, I'm skipping section 1 and section 2 because they're really kind of cool for people who really want to understand the history of computers. Okay, like back in the good old days, how do computers operate? What kind of devices are inside the computer? It's kind of cool. Okay, for people who want to go all the way back and kind of dig up how computers work. On the other hand, for people who just want to get things done, okay, we can start with this, okay? So we are going to start with transistors. This class is organized completely from a bottom-up approach, okay? Which means I'm going to start with something that is quote-unquote physical, things that you can buy, okay? Transistors or relays or whatever. You can make your own circuits, okay, that can perform certain functions, and then those are really simple function or simple gates, and then we make larger gates out of the smaller gates, and then we can make things that can add numbers, and then we can start to make things that can remember values and so on, and then we'll put the processor together about midway through the semester. And then after that, we're going to program that processor. It's a very simple processor. It has 22-ish kind of instructions. That's very small, okay? Most modern processors, most Cisp processors have hundreds of instructions. This one is tiny. And it has 256 bytes of RAM. And you can ask, what can you possibly do with 256 bytes of RAM, okay? Well, we can do Fibonacci recursively. We can do the Tower of Hanoi recursively. We can do a bunch of stuff, okay, that you would probably not think that 256 bytes is enough. So 256 bytes for the program, for the variables, and so on and so forth, everything. They all fit in 256 bytes, okay. And that's my own processor. In other words, it's kind of difficult to find resources to talk about it, outside of this class. And I read one comment on ratemyprofessors.com, a particular person complained about it. It's like, well, This pretty much makes it impossible to cheat in this class. Well, that was not the intention, okay? But I'm so sorry that that person felt that way about me using my own processor. All right, no, I'm not actually sorry. All right, so we're gonna start with transistors. There are two types of transistors. So in order to explain this, it is best for me to use Logisim, which is actually what you are going to use later today in the lab. And I just click on something that I'm not supposed to. And there we go. All right, very good. All right, so this is Logisim. Okay, there you go. So Logisim is a pretty old open source program. Okay, it's a little bit buggy. We'll talk about the bugs in just a little bit, or maybe later. So what we're going to do is we are going to build something using transistors. Okay, so you might want to take notes. Okay, and I am making sure that I am still recording. So this way, if you cannot take all the notes that you need, you just need to jot down the time. So when I release the video, which is usually right after the class, you can just kind of fast forward to the few seconds that you need for the screenshot that you want. Okay. So I'm just going to magnify. So Logisim is a little bit archaic when it comes to user interface. The zoom control is all the way down here. Okay, we are now at 100%. So I'm going to bump it up to 200%, just so that we can take a closer look at the transistors that we are going to use. And at the same time, I'm going to illustrate how to use this particular tool to make your own circuit. So to get to the transistors, I believe it is under wiring. And then you just go down here and you can go to the transistor. So these are all single clicks, okay? I'm not dragging anything, I'm only single clicking. So when you click on a particular device on the left-hand side, these are more like classes in object-oriented programming. They are used to make the actual instance or object of things. So one click to click on transistor, and then one more click on this side, on the right-hand side, the main area, you can place the component. And then we'll kind of talk about what a transistor is and what it can possibly do. So now I just have another single click. Okay, so once again, no drag and drop so far, just click. Okay, so when we look at this, the important part is the lower left portion of the screen. It is kind of like it let you look at the attributes of the device that is being selected. So in this case, we can see that a transistor has got 4 attributes. It's got 4 things that you want to know about and 4 things that you can change. So the first one is the type. Okay, this is a P type, and there's another one called the N type. There's also the facing, which is rotation. So right now it is facing east. So this particular arrow here is pointing to the east. Gate location allow you to flip the gate, which is the 3rd pin here, up or down. Okay, so it's mostly just for making things to look nice. As far as data bit is concerned, right now we're only going to use one single data bit. Okay, so there's no need to worry about what it means. Well, we're going to use one single data bit. Okay, so now the question is, what does it do? Okay, so I can illustrate what it does, okay, with a very simple circuit. So let me first do some rotational change because I want the arrow to point down. So I can go to facing and make it point south, like so. But to make it work, I also need a power supply. So you can go down to, let's see, power, okay? So power is kind of like the positive end of your battery, okay? The little plus sign, on those batteries, that's your power, okay? It provides, the source of current. And then you also need, well, in this case, I don't really need ground, but I'm going to put it on the screen anyway because I will need it later. So ground is equivalent to the negative end of your battery. So now we have positive, we have negative. Is that okay? Okay, all right. And then we're also going to have some pins, okay, PIN pins. So this is called an input pin over here, okay? This is an output pin. So these two are different kinds of pin. An input pin allows you to change the state of the pin, and then the output pin basically read what we call a node, and I'll explain that in just a little bit. So now I've placed a bunch of components onto the circuit, and I'm going to illustrate how to make connections, and also, what do we do with these components. So the first thing I'm going to do is I will connect the input pin, which is this thing here. Let's give it a name, okay? Because once we give it a name, I can just refer to it. So we're going to call this pin X, okay? For no particular reason. I have been starting to use the letter X way before Elon Musk, okay? So he cannot complain about that. He can keep the name macro hard, if he wants. Do you guys know about that? What is macro hard? Nobody knows? Yeah, it is a nameplate off of Microsoft because Elon Musk believed that Grok, his AI engine or AI model, is so smart that it can replace developers entirely. So he can have a software company that uses AI to replicate everything that Microsoft has. Okay, so there'll be Windows, the entire Office suite of products, Outlook, all the server products and whatnot. And because he wants to be smart, so he decided, I'm going to choose a name that is the opposite of Microsoft. Let's see, what is the opposite of micro? Let's choose macro. And what is the opposite of soft? It's hard. So Macrosoft was his choice for the name of his company that he plans to use to compete with Microsoft. Now, I'm pretty sure he's a smart man, but as far as the name is concerned, I think that's about the name that the second grader would come up with. So he might need to work on the marketing part just a little bit. Maybe ask his own AI model, what would be a good name for a company that is replicating what Microsoft is doing. But let's make it not something that reads like a second grader can come up with. That would be a great prompt. All right, anyway, I digressed. I do that a lot. All right, so now we're going to make connections. So one thing about LogicSim is you can draw a wire, okay, from anywhere to anywhere else. Okay, I shouldn't say that. So you can draw a wire from here. Oh, okay, I take it back, you cannot do that. But you can start with yes. So you have to start with a terminal, and if you are hovering over a terminal, you can see a circle. Now, if it doesn't appear as a circle, you're not over a terminal. So in this case, I want to connect this terminal to this terminal over here. So I can now this time I am dragging, okay? So I'm dragging from here all the way to here. So now we have a connection from the input pin to what we call the gate of the N-type transistor, or this is the P-type transistor. Excuse me, I made a mistake there. Okay. So with an input pin, you can do a few things. Now, if you switch from the selection tool to what I call the poking tool, now you can experiment, okay? You can go use the poking tool and change the state of an input pin. So you can see that dark green is a 0, bright green is a 1, okay? So for anything that is just binary, you can tell the state just by looking at the color, okay? Are we good so far? All right. So you go like, yeah, but it doesn't seem to be doing anything. Well, you're correct. It's not doing anything. So let me make a connection here. So I have to switch back to the selection tool to draw another wire. This time I'm going from the positive end, or you can say it is an endless source of positive charge, and I connect it to the source pin of the P-type transistor. Okay. And now I can also just kind of switch the state of the input pin. Remember to go back to the poking tool, and you go like, oh, I can see something. I mean, I can see the other end changing the color. So now the question is, what does blue mean in this case? Because we can see the output pin is blue it says X, okay, once again, has nothing to do with Elon Musk. And we can also see the bottom part of the transistor is also blue. Blue means it is floating, okay? You can write it down. It's actually a technical term because floating means it is neither a 1 nor a 0. It is undetermined, okay? So think of it this way, okay? Think of it like, let me choose a prop here. Even though this box says, PCS faculty, probably there's a hidden only, somewhere on this piece of paper. So think about this lever, okay, as spring-loaded. So in its natural state, it is like this, okay. So if I want it to be a 1, okay, I can try to change the state. I have to exert some force to change it to a 1. So let's just say that your right-hand side is 1, okay. If I want to change it to a 0, I have to exert some force, to push it to the 0 side. But if I don't exert any force, it's just kind of standing in the middle. Is that okay? That's what floating means, okay? And in this state, it is blue, okay? So blue simply means there's nothing of any charge attached to that particular conductor, okay? So it's neither positive nor negative. It's just kind of hanging around, all right? So now, if I change the state of the input pin to a 0, you can see that, oh, it changed into a 1, okay? In other words, the transistor is making a connection. It's completing the circuit from the source of positive charge or an infinite amount of 1s to the output or the other side of the transistor. Are we doing okay so far? Okay, if I change the state back to a 1, it stops the flow, okay? So the output is turned off. So one thing you can do is to just think of a transistor as a valve, okay? Do you know what is a valve? At some point in time, people will tell me, I don't know what is a valve. Yes? Yeah, so it's kind of like the faucet, right? It's kind of like a faucet, when you're in the kitchen, okay, for instance, and you want to wash something, then you have to quote unquote turn on the valve, turn on the faucet. So what it does is it allows water to flow from the water line, which is under a lot of pressure, right, to come out of the end of the faucet so that you have access to the water. And you say, okay, I'm done with washing my dishes. You just turn off the valve, right? Then there's no water coming out because you're blocking the water from coming out, even though the other side is still pressurized, but you close the valve, or I should say you disconnect, right? You disconnect the water from the source of the water. Are we good so far? So a transistor is like a really fancy version of a valve or a faucet like that. You can turn on or you can turn it off, okay? When you turn it on, it is connecting, it is allowing things to flow through it. If it's disconnected or when it's off, it simply disconnects and disallow flow through it. Are we okay with those concepts? Okay, all right. So now we're gonna hook up this wire, or hook up a wire, use a wire to connect this end of the transistor to the output pin, which is really not necessary, but I'm just gonna do it anyway. So right now the output pin, which I can just give it a name. So let's go ahead and give the output pin a particular name. I'll just call it A, okay? So output pin A is now quote unquote floating because the transistor is turned off. The transistor, or this P-type transistor, is turned off because the input or the gate is a 1. All right? So you might say, but I cannot possibly remember all this stuff, okay? This is kind of complicated. So the good thing about LogicSim is there's a built-in help. So if you go to help, you go to library reference, and let me show you what it looks like. Unfortunately, it opens the window on the other side, so I have to kind of move it back to this side. So when you go to the library reference, it has exactly the same structure as what you see on the upper left-hand side of the main LogicSim screen. So now you go to wiring, and you can see it also has exactly the same organization. So now you can go to transistor, like so, and it will give you all the explanation of what a transistor is, how to turn it on, how to turn it off, what is the N-type versus a P-type, and so on. So it is really crucial that you know how to look up the information because it is already there. Okay, it just makes it a little bit easier for you guys to kind of like, okay, I cannot remember what is a P-type transistor, how do we turn it on, and how do we turn it off. This is how you can look up pretty quickly. Okay, so what exactly are the rules? Okay, there is a truth table down here somewhere. There we go. So it's a truth table, and so Z is floating. Okay, Z is basically floating. And let's see. So the source is whatever is coming from. Okay, within these two pins. When you see the arrow pointing this way, when the arrow is pointing from left to right, the left-hand side is called the source. Is that okay? So it all depends on the arrow. Okay, if the arrow is pointing from left to right, the left side is called the source. The right-hand side is called the drain. Okay, so you have source going to drain, and then the pin that is sticking up, the third pin, is called the gate. So what this diagram is showing you, or what this table is showing you, is if the source is a 1 and the gate is a, let's see, and the gate is a 0, then the output is a 1. Let me say that one more time. If the source is a 1 and the gate is a 0, then the intersection of the row and the column is the state of the drain. Is that okay? Or do you want me to kind of explain it in a slightly different way? Hmm? That's the nature of the device. Okay, that's just how the device functions. So this class focuses more on the logical operation of a transistor and not so much into the device physics of the device, because there's a whole upper division electrical engineering class on the device physics. Okay, and I'm not qualified to teach that at all. Okay, but I can read a truth table. Yep. So okay, think about this as a function. Okay, so what are the parameters? Okay, what are the inputs into the function, and what is the output? The output is the state of the drain, which is where the arrow is pointing to. The inputs, there are two inputs. Okay, there are two things you need to tell the transistor, and it'll give you an answer. Okay, so the two things that you need to quote unquote input would be the source, which is where the arrow is coming from. So in this case, it's the left-hand side, and also the gate, which is the third pin. So the input is always, the source is always where the arrow is coming from. Because you can rotate the device, so what is left right now can be top, can be bottom, can be the right. Okay. So that's the P-type transistor. Okay, so the P-type transistor has its own table, and then the N-type transistor has a kind of like an opposite table. Okay, but it's a different table. So are we okay so far? Do we have any questions of how to read the truth table? Yep. So Z is representing, remember what we said about floating, right? So Z is representing float, which means, well, we don't know what the drain is going to be, okay? Or you can basically think of it as the default state, okay, nobody's pushing it one way or the other. That's what Z is. It's representing the floating state, okay? The X is representing unknown, okay? It means, we don't know what it is, okay? Are we okay so far? All right. So for the most part, we don't really have to worry about that because the only time X particularly, so the only time we don't have to worry about X is when the input or when the source is neither a 0 nor a 1 nor a Z nor a kind of float. Then we don't know what we don't know what the drain is going to do. Okay, that kind of goes without saying. Are we good so far? Okay, so the really usable portion of the truth table would be just this portion here. Okay, this is the only portion that is useful. All right. So now the question is, okay, here's the next question. How can you tell a P-type transistor from an N-type transistor? Now, I think most of you cannot see it, okay, on this screen. So what I'll do is I'm going to put the documentation aside, and then I'll go ahead and make another transistor. Okay, so I'm going to pull another transistor, and we'll just kind of stash it over here. But this time, I will turn it into a N-type transistor. So I'm going to ask you guys, how can I do this? How can I turn an P-type transistor into an N-type transistor based on what I just talked about? So I'm not expecting you guys to be experts of using logic-sim, but I gave you guys some clues. Yep. You change some properties about the transistor, okay? So which portion of the screen can I possibly change the property of the transistor being selected? Yes? Exactly, okay? So the area that dictates or allow you to change the property of a transistor or whatever thing that you have selected is this portion here, okay? I mentioned that probably around 10 minutes ago, okay? So now we go to the type here, and then all we need to do is to use the drop down and change the P type to an N type. Okay, so now we have an N type. Did you guys see the difference? Okay, so just like any good optometrist, I'm going to say N type, P type, N type, P type. What is changed? The dot. That's right. So a P-type has a dot, okay, this little dot here. The P-type has a dot, the N-type does not have it. Are we good so far? Okay. What would that do? Well, I think I pre-answered that question. It changes from this truth table to this truth table here. Okay? So, how do we remember all of this stuff? Well, there's one thing that's relatively easy to remember. If it is a P-type transistor, you want the source to be connected to positive charge. P for positive, okay? What do you think the N-type transistor wants the source to connect to? Negative or ground, okay? So that's a quick and easy way to remember. Then what about under what condition is the valve on, okay, meaning it's connecting, and under what condition is it off, which means it's not connecting? You want the gate to be opposite to the source, okay? When the gate is opposite to the source, the valve is on, which means it is connecting. On the other hand, when the gate is the same as the source, then the valve is off, which means it is not allowing flow to flow through it. Are we good so far? Okay? All right. So without any additional discussion, I'm going to finish the circuit. Okay? So let me go ahead and finish the circuit, and then we'll talk about it. So the circuit, I'm just going to remove a bunch of stuff here. And as I build the circuit, I'll also explain some of the shortcut stuff that you can use. It's not essential. It's just easier to make things. So here I have a transistor. I'm going to rotate this, okay, just because I like things to flow or kind of align in the right direction. So I'm going to make the facing south just like last time. I need one more, okay? I need one more of these P-type transistor. So you can do the same thing that I just did, go back to the transistor, give it a click, and then go back to the main area and click it on in the main area. You could do that, okay? But the easier way to do this is to type Control D on the keyboard. Control D for duplicate, okay? And if you are still learning all of this stuff here, it's okay. Go to Edit, and you can see duplicate has a shortcut key of Control D. So Control D, it gives me a new one. I just have to drag it to a different location like this. But for this one, I want the gate to be on the other side. So which property of the transistor do I use to move the gate to the other side? Gate location, okay? Gate location will do that, okay? So now we just kind of go to gate location and say, I want the other side, like so, okay? Now once again, this just make it look nicer. It doesn't really change the functionality of the transistor. It just kind of make it go like, oh, okay, it just looks nicer this way. So now I need two N-type transistors. So I go to transistor again, pull out another transistor here. First thing I do is to turn it into an N-type. So remember, okay, so let me give you a quick quiz here. How do I want to connect the source of an N-type transistor? Should I connect it to the positive source or the negative source? Negative source, N for negative, okay? So that means if I want the diagram to look nicer, I want the orientation or facing to face which way? I want it to face north, okay? Because I want the source to tie to ground, okay? So I want this to be north like so, and do it like this. And I'm gonna need another one. So I'm gonna give myself a little bit more room to have another one. So I'm gonna give myself another one. And if I just want another one of the same orientation and the same type, what do I do? What is the shortcut to do it? Control D, okay, and D for duplicate. Very good, okay. So if you think that your short-term memory may not be able to retain all of this until the time of the lab, what do? You just think, I can ask Tech again. And what do you think Tech is going to tell you? Exactly. Or worse yet, I just tell people, why don't you watch the lecture again? So if you don't want to hear those kinds of answers, because I will give you those answers, what do? You drop this class and just take the Folsom Lake version of this class. That's what most people would do. But do you think that's going to help you with all the other classes in a 4-year university? I'm not going to give you the answer because I don't want to imply anything of my colleagues in a different college. So what do? What do? You take notes, okay? If you see something that is new and go like, okay, this seems important. I might need to remember that, write it down, okay? You can write it down, you can type it, okay? Or you can just write down the time of, when I start to mention this, because this is all getting recorded. All right, so Control D, there we go. So now we move this a little bit up here, like so. All right, that is kind of cool. I think I have pretty much everything that I need. I need one more input pin. I'm gonna stash it down here. Okay, there we go. And I'm gonna need an output pin. I think this would be a good place to put it. All right, so I got my circuit here. So for this particular circuit, the orientation of the transistor is important, okay? And then the type of transistors is also important. We have two N types here. We have two p types over here. Okay, so now we go for the connections. And so the connections is kind of just go like here to here, and then here to here. So the red color means X, okay, which means it's not a 0, it's not a 1, it's not floating. I have no idea what it is, okay? That's what red means, okay? So and then from the top, I'm gonna connect here, right here, to here, and then from here to here. There we go. And you can see there's a gigantic dot here. The gigantic dot means it is actually connecting, okay? So later on, we'll see something that is not a gigantic dot at quote unquote a junction. That means it is a flyover as opposed to an actual connection. All right, so we're gonna put it here like this. Okay, there we go. Put it over here. Connect this all the way here. All right, so now we're gonna go for some interesting connections like this. And I'm gonna put this one over here. And I'm gonna put this over here. And now I'm gonna illustrate what a flyover looks like. This is a flyover. So a flyover, you can see there's no gigantic dot here. So that means the horizontal one and the vertical one, they are not actually connected, okay? One is a overpass of the other one, or you can say the other one is an underpass of whichever one. All right. And I'm almost done. All right, so let's go ahead and connect this all the way up here. And there we go. All right. So let me give you a warning first, okay? The one that you need to draw in the lab is not this, okay? This is a portion of it, okay? But the input-output is a little bit different, okay? So I just want to warn people about that. Okay, so you can see that there are two input pins. Each input pin is either a 1 or a 0, a bit, right? So we have two of those. So what I'll do, just to illustrate the concept that you need for the lab, I'm going to use a splitter to merge the two input pins into one single input pin that have 2 bits. But then I have to split the 2-bit input pin back into the individual bits before I can feed to the gates. All right, so I'm going to move the whole thing a little bit to the right-hand side. Okay, select everything, and then just kind of move it a little bit to the right-hand side, like so. All right, so I'm going to take out these pins over here and make another input pin. So this is the input pin, but it's going to be a 2-bit input pin. So how do I turn a 1-bit input pin into a 2-bit input pin? Of all the properties related to the pin that is being selected, which one do you think has to do with the width of bits? Data bits, okay, very good. Okay, so it's the third item from the top, data bits, okay? That allows you to change a 1 input pin bit into a 2-bit input pin, just like that, okay? So that means whatever is coming out of this, what we call a port here on the right-hand side, is no longer representing a single bit, which is a 0 or 1. It is now representing 2 independent bits. Each one can be a 0 or 1. Is that concept understood? Sort of? Okay. I can see people kind of shrugging their shoulder. Okay, yep. Yep, if you turn it into 3 bits, it will show you 3 bits, like so. But in this case, we only need 2. Okay, so we're gonna go back to 2. But you can leave something that is not used, okay? So I'm gonna do some tricky stuff here and just make it a 4-bit, okay? You go like, but TAC, we don't need 4 bits. Yeah, we don't need 4 bits. So how do we just kind of single out the ones that we need? Okay, that becomes the next question. So of the upper left window of all the devices that is being shown, which one do you think has the ability to break up something that is multi-bit so that I can have access to one or the other. Splitter, very good. Okay, so we can totally play that game. What is the game where you're only allowed to use a word to describe something, and then the other person has to guess what you mean by that, and then you have to single out certain things. Is it called encoder? Hmm? Codename. Yep, that's it. So we can play that game in this class. That's exactly what we are doing here. All right, so splitter it is, okay? So the splitter can do this, okay? So now we pull a splitter, okay, out of the upper left portion. It looks like this, okay? Without me explaining this, and I tell you that one end is called the merged end, the other end is called the split end, can you tell which end is which end? So which end is the merged end, left or right? Left, okay? Which end is the split end? The right-hand side. Okay, very good. So the left-hand side in this case is called the split end because how did you tell? How can you tell that it's called the split end? Because it's got multiple wires, right? And then the merged end has one single wire. Okay, so what we'll do is we're gonna kind of drag it down here. Oh, before we do that, you can also see a splitter has got multiple properties, okay? Has got multiple attributes. Phasing, once again, is just rotating it so that it looks nice in the whatever diagram you want to draw. Fan out is controlling the number of split end that you have, okay? Then you go like, okay, if we have fan out, why do we still need bit within? Bit within is controlling the number of bits of the merged end. Let me say that one more time, which is usually a clue that you might need to write it down. The bit within for a splitter controls the bit width of the merged end. Because if you don't have the correct bit width for the merged end, you cannot make proper connections to something else that has a different bit width. Are we good with that concept? Yes. Yes. So let's go ahead and play with this a little bit, okay? So let's just go with 6 over here. So if I go with 6, it will automatically try to make a it will try to make an even break, okay? So you can see with 6 bit in the merged end and only a fan out of 2, what do you think it's going to do? It will try to do an even split, which means 6 divided by 2 is 3. So that's why we end up with 3 bits on the top and 3 bits on the bottom. Okay? How can you tell? Okay? So let's go ahead and magnify this just one more time. Do you see 0 to 2, 0-2 on one of the split end and 3-5 on the other split end? Okay? So let's count. 0, 1, 2. Oh, there are 3 of them. And then we have 3 to 5, right? 3, 4, 5. There's 3 of them. So that's how a splitter works, okay? Now this is by default. What if you go like, you know what? I only need bit 0 on the top and bit 1 on the bottom. I don't need the other bits. They're just totally useless for whatever I'm doing, okay? So let me go back and select the splitter again. Let me repeat what I want, okay? I still want 2 split end, okay? Except the top split end, I only want it to be connected to bit 0 of the merged end. And I want the bottom split end to only connect to bit 1 of the merged end. So looking at the lower left-hand portion of the screen, looking at the attributes of the splitter, what kind of things will you click on just to find out whether it will do the job or not? Which portion are you going to click to go like, I think it is this one. Let me go play with it a little bit. Okay, I can repeat the question. The question is, if what I want to do is the top split end to only connect to bit 0 and the bottom split end to only connect to bit 1, and all the other bits, the other 4 bits, I don't even care. Okay? How can we get that configuration based on the lower left-hand side of the screen? So, okay, let's just rule out the things that we don't think has anything to do with this, okay? Do you think phasing has anything to do with this? Because that's just rotate the thing, right? How about fan out? We still want a fan out of 2. Remember, I want 2 split end. So that's why we still need a fan out of 2. Are we going to change the bit width in? Remember earlier I said you might want to write this down? So what does bit width in control? Merged end, right? It controls the bit width of the merged end. That doesn't seem to do what we think we need to do, right? So what is left? Yes. Exactly. So let's click on one of them to look at the 3 options that you have for every bit of the merged end. Then we can go like, oh, so that's how we do this. Okay, click on one of them because they all look the same. Okay, what do you think none means in this case? It doesn't connect to any split end. And what do you think top means? It connects to the top split end. At the bottom means it connects to the bottom split end. Is that okay? So let's do exactly what we want to do right now, and then I'll give you some really funky configuration. So now I want this to be top. Okay, just click on the wrong thing. And I want this to be the bottom. And then suddenly, you see something that is kind of odd. Because you can now see the top split end says 0, 2 instead of a dash. What is the difference between a 0-2 versus a 0, 2? One is not included in the case of a comma, right? A comma means, oh, we are just using bit 0 of the split end and bit 2 of the, bit 0 of the merged end and bit 2 of the merged end, and both of those are connected to the top split end, okay? So that means, oh, okay, so I think we know how to get the configuration that we need. Click on this again, and this is all we need. Everything else, just don't connect to any of the split end. So that's how we do this. All right. So I can see that not everybody is frantically copying or writing notes. That's okay, because you got backup here, okay? So let's just say that you walk to the lab and you totally cannot remember a single thing that I just said. What are you gonna do? You can watch the video, but that takes a little bit of time. What else? Drop the class, okay? So I do not recommend that, but if that is how you want to do it, sure. What is the third option? Talk to someone who have taken notes. And the fourth option? Exactly. Okay. So now I don't know about you, this is a personal thing. I want myself to be as independent as possible. I don't want to rely on anyone whatsoever as a student. Okay, it's the truth. Okay, that is actually the truth. So this is how you do it. Okay, you just use the same tool that we were looking at before. Click on Splitter, and it will give you the same information that I just gave you. Okay, so learn how to use this tool. Okay, learn how to read. Okay. Yes, I know you guys know how to read, but there's reading and then there's reading, okay? Reading text that is filled with emoticons and abbreviations is not reading, okay? This stuff is more like actual reading, All right, so getting back to where we need, okay? So let's just say that I would go like, okay, I think this is gonna work. Well, it's not gonna work because the merged end in this case has 6 bits, right? Because according to the property of the splitter, the bit within, which is controlling the number of bits of the merged end, there are 6 of them, okay? And how many bits is our input pin? Okay, let's just say that you're totally not convinced that it's 4-bit. Okay, how do we make sure? Click on it. Okay, so you use the selection tool, you click on the input pin, you go like, oh, so this thing has 4 data bits, but this thing over here has 6 bits. Okay, you know what? I'm gonna try to connect it anyway. Okay, because I have seen people who try to jam a wrong connector to the wrong plug. It's like, if I force it, it's gonna work. So we'll give that a try virtually. Okay, we're gonna go like, yeah, this is gonna work. Nah, not gonna work. Okay, so I'm just gonna, I'll try to hide the error message here, which I really can't. Okay, so you see the orange wire and the circuit is not working. What are you gonna do? Drop the class or something like that. No, you read the error message. You read the error message. It says incompatible with. Okay, how incompatible? I cannot see anything wrong with this connection here. It even tells you one side has 4 bits, the other side has 6 bits. Do they look the same to you? Does 4 look like 6? No, that's why they're not compatible. Okay, so we need to change one end or the other. Okay, we either change the input pin or we change the output, or we change. Excuse me, I take it back. We either change one end, okay, and we change the input pin to be a 6-bit input pin, or we change the splitter so it has only 4 data inputs. Okay, so that's what we're going to do. Okay. So we go back here and we say, okay, 6 is going to work out here. We'll change it to 4. And then you will be kind of annoyed by what is going to happen next. Okay, so watch very closely. Okay, you go like, the tool is being too smart. Okay, it's being too smart because as soon as you change bit within to 4, it goes like, oh, let me help you rebalance all the bits to the output end. 4 divided by 2 is 2. So I'm going to send bit 1 and bit 0 to the top, and then bit 2 to bit 3 to the bottom, even though I didn't want it to happen. Yep. Say again? So, okay, can you repeat that again?
So those split answer too, because it's both 0, 1, and 2, 3, those are merged as well.
Yep.
So we can like daisy chain.
You can daisy chain splitters. Yep. Does everybody understand what is daisy chaining? Okay, very good. So what we can do here is, one, we can daisy chain. So let's do that because it just looks funky. I like that. Okay, so we're gonna daisy chain. We just pull a default splitter here. This is a default splitter. A default splitter says it has 2-bit input and has a fan out of 2. The top is going to bit 0. The bottom is going to bit 1. Looks kind of like exactly what we need, right? So what we do is we just do a Frankenstein on this. Bing. Okay, so bit 0 coming from the input pin and bit 1 coming from the input pin, these two will be over here, and that in return connects to another splitter to split bit 0, bit 1 into, guess what? Bit 0 and bit 1. So that's how we're going to do this. Okay, now you don't have to do it this way. This is really just my example of doing this in a more extremely kind of awkward way, but it does work. Okay, so I just have to look at the time because I want to finish I want to finish talking about how this entire thing works. So with this one, I can just loop around the whole thing, get it down to here, and connect it over here. Now this is probably a bug of Logisim. It does this sometimes. Hold it by intention. Okay, so we'll go ahead and reset simulation. Okay. There we go. Enabled, reset again. Okay, there we go. So sometimes it does kind of do a hiccup like this. The best way is to save the circuit, get out of Logisim, come back in, reload the file. Okay. Now, when you look at a file that is a Logisim circuit, most people just want to double click on it to open it. It doesn't work. You have to open Logisim, inside Logisim, go to File, go to Open, and open the file. Okay, so double clicking on the Logisim file does not open it. Are we understanding what that means? Okay, all right. All right, so now that we have this whole thing configured, we are now going to take a look at, but what does it do? Okay, this is, we got the circuit done. And by the way, your circuit is pretty close to this, but not exactly, okay? All right, so exactly what does it do? Why does it output a 1 at this point? So what you need to do is to think about from the perspective of each transistor. Is it on or is it off? Okay, so we are going to single out the transistors and then we'll try to figure out which one is on and which one is off. What I'll also do is I will give these transistor names. So I click on one and it doesn't give me a place to type the name. Okay, fine, we'll just use the text tool here. Okay, this is Q1, this is Q2, I'll call this Q3, and then we'll call this one Q4. There we go. It's just so that we can refer to each transistor by its name. And this one, I clicked the shift key accidentally, so we're gonna have to, there we go. Yep, this is Q1. There we go. All right, so we want to look at Q1, and the question is Q1 on or off? In other words, is it allowing stuff to flow from the source to the drain? Yes, because the drain and the source are opposite to each other. Okay, now how can we possibly tell that the gate is opposite to the source? By the way, which one is the source? Where is the source of a transistor? How can we identify the source of a transistor? So if you're looking at your notes, that's a good sign. If you, yep, it's where the arrow is coming from. Okay, so that means for Q1, okay, I'm just going to point out using a mouse here. So for Q1, this is the source. If that is the source, where's the drain? The other side, exactly. So this is the drain. And where's the gate? That's a stupid question, but I'm asking anyway. It has only 3 ports, right? 3 pins. We have identified the source. We have identified the gate, the drain. So where do you think is the gate? Whatever I haven't mentioned, I have not mentioned, right? So this is the gate. All right. But tech, how can they possibly tell that the gate is opposite to the source? Okay. The colors, very good. Bright green means 1, and then dark green is, so 1 and 0s are quote unquote opposite because you can look at 1 as true, 0 as false. Okay, so they're opposite. So whenever they're opposite, the transistor is on. Okay, when the transistor is on, it allows whatever is at the source to go to the drain. We good so far? All right. So Q1 is on. What about Q2? Is also on, right? What about Q4? Is Q4 on? Look at the source and look at the gate, okay? So this time, where is my source? Yep, it's the southern side of Q4. This is the source. How can I tell it's the source? How can we identify the source of a transistor? It's where the arrow is coming from, okay? See this arrow here is going from here to here. So where it's coming from is the source, where it's going to is the drain, the remaining pin is the gate, okay? With this one, can we tell that the gate and the source are not opposite to each other? Can everybody tell for Q4 that the source and the gate are not opposite of each other? How can you tell? They got the same color, okay? They're both dark green. Now, even if you cannot remember, is it dark green a 1 or a bright green is a 1? It does not matter, okay? Dark green is dark green. Dark green cannot possibly be different or opposite to dark green. Are we good so far? Okay. So if Q4 is off, what does that mean? It's disconnecting from the source to the drain, right? So that means the drain over here is now not connected to the source. So that's why the drain is blue, okay? Tell me again, what does blue represent? Floating, which means nobody is specifying whether it should be a 1 or a 0. It's just hanging around, okay? Are we good so far? Sorta, okay? So, which is, according to the truth table, what letter is representing floating? We talked about that. Z, that is correct, okay? So that means for Q3, from the Q3's perspective, the source is a Z. It's an N-type transistor, the source is a Z, the gate is a 0. Using the lookup table, I should be able to tell that Q3 is not doing anything with its output, okay? So let's go ahead and take a look at the truth table because I want to make sure that you know how to read the truth table for a transistor. So I go back to the transistor, go all the way to the truth table, okay, like so over here. And we are dealing with an N-type transistor because there's no bubble, where the gate is. We know the source is a Z, and we know the gate is a 0. Is it 0? Yep, it is a 0. So that means we are looking at this column here and this particular row here. The intersection is a Z, which means the output of Q3 or the drain of Q3 is also not specifying either a 1 or a 0. Okay, so you look at the diagram. Okay, so let's go back to the diagram here. You go like, but how come this is not blue? Okay, we are supposed, Q3 is not supposed to be specifying the output in any way. Why is it not blue and instead it's bright green? The bright green is coming from the top because Q1 and Q2 are both on. They're both connecting the positive end to this particular connection here. And that's why that is bleeding to the output of Q3. And this is also why the output is a 1. Are we good so far? Okay. So let's just say that tech is irresponsible and doesn't really quite tell you what this little circuit is going to do. And I'm going to tell you the input can only be a 1 or 0 per bit. Okay. So how many possible configurations of the input do you actually have to test out in order to try to figure out what this whole circuit is going to do? Not exactly 2. It is related to 2, but it's not 2. 4, okay? It's 2 to the power of 2. Because each input bit can either be a 1 or 0, but because we have 2 of those, so you have a truth table that have 2 bits, okay? With 2 bits, you have 4 possible combinations, okay? So we're going to spell out all 4 combinations, okay? So I'm going to make a table. Can I do it here? I can, but I don't want to. So let me use a text editor to make that. Mousepad. Okay, there we go. Okay, so I'm using this kind of like a note-taking device. Okay, so we are going to look at the 4 possible inputs, and then we look at the output. Okay, so the 4 possible inputs would be 0, 0, 0, 1, 1, 0, and 1, 1. Those are the only 4 possible inputs. You go like, but what about the other 2 bits of the input pin? They're totally ignored, okay? Because those are not coming out of the split end at all. So they're just kind of like not doing a single thing. Okay, so we have just figured out the output of 0, 0, 1. The output of 0, 0 is a 1. Okay, we just figured that out, and we'll just kind of give it some name over here. This is X, this is Y, and the output we'll call that A, like so. Okay, what about 0 and 1? Okay, in other words, now I need your kind of like, I need to turn your brain into Logisim so that you can simulate the circuit. So I'm going to turn off simulation, and some of you will occasionally mistype on the keyboard and turn off simulation. Just turn it back on if something happens. Okay. So now I'm going to turn the input to exactly 0, 1. So can someone tell me what the output should look like? And you had a question? Oh, okay. All right. You were just stretching. Okay, that's okay. All right. So it's 0, 1, okay? So that means bit 0 is a 1, okay? Because this is the least significant bit. It is always to the right-hand side. This is bit 1 over here. So this bit 0 is going to be this bit 0 here. So we know that, okay, this entire wire is going to be 0. It's going to be a 1. Okay, so if this is going to be a 1, we can see that it only affects Q4 and Q2. So let's start with Q4. Okay, if the highlighted node is a 1, is Q4 on or off? It's going to be on. Very good. And what about Q2? It's going to be off. Okay, because if the highlighted node, okay, this is called node. When a bunch of wires are electrically connected, it is collectively called a node. Okay. Okay, so Q4 is on, which means this is connecting, but Q2 is off, which means that path from the positive side is not connecting. Okay, that's one configuration, that's one thing. So now we look at the other node, which is this one here. This is for bit 1, which is a 0. So can someone tell me whether Q1 is going to be on or off? Q1 is going to be on, and then Q3 is going to be off. Okay, very good. So the transistors that are on is almost as if it's just a straight wire connecting. Okay, so that means in this case Q4 is on, so that means this end and this end are just connected, but Q3 is off, which means for all practical purposes, it is as if Q3 is not even there. Okay, which other transistor is off in this case? It's Q2, right? Q2 is also off. So it is as if Q2 is not here. Okay, so what do you think is the output? The question you should be asking is the output pin, which we call A over here, does it have a path to connect to the positive end? It does, right? Because Q1 is on, okay? Does it have a path to connect to the negative end? Well, just follow the wire, okay? Does it have a way to connect to here? So you go here, you go like, I'm gonna make a left turn. Nope, no go. So it does not have a path to negative. It does have one path to positive. So what do you think is the output? Is it a 1 or a 0? It's a 1. Yep, okay. All right, so this is going to be a 1, and this is going to be a 1. Then you already know what the last one is going to be, okay? Yep, it's going to be a 0. You don't even need to know the circuit, okay? Out of a truth table, okay, of 4 entries, 3 are 1s already. Don't you think if the last one is also a 1, the circuit doesn't do jack, right? So it has to be a 0, okay? But we're going to try to figure out why it is a 0 in this case, okay? So I'm going to undo the deletion over here, and this time I am going to specify 1, 1 as the input, okay? So if bit 0 is a 1 and bit 1 is also a 1, that means every single gate is seeing a 1, right? We already know that a p-type transistor configured this way will turn itself off when the gate and the source are both 1s. So that means Q1 and Q2 are turned off. Okay, there's no path left to connect to the positive end. On the other hand, let's look at Q3 and Q4. We'll start with Q4. Okay, so because the gate is a 1, the source is a 0, they are different. Q4 is turned on, which means whatever is at the source is now connected to the drain, which means the drain of Q4 is also just ground or negative. Is that okay? So knowing that the drain of Q4 is ground or 0, it goes into the source of Q3. Is Q3 on or off? It's on because Q3's source is a 0, the gate is a 1, they are different, so Q3 is also on. What does it do when a transistor is on? It makes a connection. So it is as if Q3 is not here and replaced by a single wire to make the connection from the source to drain. So this means Q4 is on, the ground goes through Q4 to Q3. Q3 is also on, which means the ground is going through Q3 to the drain of Q3, which then connects to the output pin. So in this case, the output is a 0. That's why it is a 0. Yep. Say that one more time. Okay, so that is a disastrous situation because it's also called a crowbar, and I'm not kidding. Okay, crowbar is an actual term in electrical engineering. It is the same thing. Now, do not ever do this, but I'm using an example to illustrate it. It is as if you have a jumper cable for jump starting your car, and you're connecting the cable from the positive end to the negative end of the battery. Don't do that, okay? Bad things will happen. It's called a crowbar because what it will do is it will create an immense amount of heat. It will melt the insulation of the wire. In some cases, your wire may even glow depending on the length of your jump start cable, because your car battery actually can support enough current to kind of make it glow. Yeah, don't do it. All right. So this is all good. Okay, we are almost done with this illustration. So now we have a logic gate that is kind of like this. Okay, so if I just use a symbol to represent, we can look at a gate like an operator. Okay, like a logical operator. Let me just see if you guys remember all this stuff, because for those people who do not remember this, you might need to refresh your memory. Okay, what is 0, ampersand, ampersand 1? Say again? It is 0. The result is a 0 because ampersand, ampersand is a logical AND in CISP 360. Okay, so I'm going to make a new symbol. Okay, let me see what symbol I want to use here. I have to use one that you are not familiar with, and it has to be on the keyboard. I am going to use $sign here. Okay, so I'm going to use $sign to represent the operation here. Okay, 0, ampersand, 0, $sign 0, $sign 1, $sign 0, and then finally we have $sign 1. And we know the result already. Okay, this is a 1, this is a 1, okay, this is a 1, and this is a 0. Okay, so now we go like, do we have a logical operator that would do exactly that? The answer is, if you give me one more operator, we can do it, but there's no one single logical operator that will give you this result. Okay, because what we are seeing here is basically the same thing as the negation of 0 and 0. And we are looking at the negation of 0 and 1. And this is the negation of 1 and 0. And this is the negation of 1, whoops, and 1. Okay, so for those of you, now I really want people to think in the sense of, what if tag is wrong? How can they possibly tell the tag is wrong? In other words, can you evaluate the expressions on the right-hand side of the equal yourself? Okay, so now you go like, oh, okay, so they are really the same. So you cannot use a single logical operator to describe the circuit that we just made, but you can use two, okay? In electrical and computer engineering, this particular logical operation is called NAND, N-A-N-D. The first N stands for negated, because it's a negated and, negated and. Okay? In short, it is called a NAND gate, N-A-N-D gate. Okay? So you go like, what does it do? This is the truth table. Okay, cool. But who's going to use a NAND gate for anything? Okay, just about everybody. Okay, because in computer engineering and to a certain extent electrical engineering, the simplest gate that you can make is either a NOR gate, which is a negated or a negated AND gate. This is the smallest and easiest logic gate that you can make. And you guys go like, but it is not a NOT gate, it's not an AND gate, it's not an OR gate, and those are the only three operators that I know from CISP 360. How can this be possibly useful? What if I tell you you can make a normal NOT operator using NAND? What if I tell you you can use a bunch of these NAND gates and make a regular AND, and you can also use a bunch of these to make a regular OR? In other words, if I want to make a new programming language where it has the minimum number of logical operators, NAND is all I need. Because with NAND, you can make negation, you can make conjunction, you can make disjunction. It can make all of the other operators that we know of. Okay? So I just talked about this. Where do you think you can possibly find out how to use NAND gates or NAND operator to make up the other logical operators that you know? Remember the link in the announcement to the reading material? Do you think that's a hint? Yep, it is all described there. Okay, so if you have read the reading material ahead of time, you would have felt asleep in this class, because this class, this lecture, would have been so boring that there's nothing new whatsoever. Okay, so are you guys kind of convinced that it might be a good idea to read ahead of the class? Let me pose the question in a slightly different way. Do you want to graduate from a four-year university? Okay, well, there's your answer right there. Okay, because if you don't learn the skills to read ahead of time and to take notes and get all this stuff down before you leave ARC, you might find a four-year university challenging. Now, does it mean that everybody's going to experience that? No. Some of you are going to be breezing through a four-year university. Even if I gouge your eye out and poke your ears in, you will still be graduating with like a 4-point-something GPA. Okay? There are those people, and I know those people in this class. But for the rest of us, mortals, unfortunately, we have to rely on study skills to an extent. Okay? All right. So I'm going to give you the lab. Okay? So this is how I set up the labs. The lab is going to be in STEM 301, the main lab. So I will show you what I usually do to set up the lab. Let me get this out of the way. Go back to here. All right. Oh, wait, before we go any further, okay? All of this It's explaining things that I just talked about. Okay, so they're all here. Okay, I know we are gonna go a little bit over time here. So for those of you who look at all this stuff here and go like, I cannot read stuff like that, what are you gonna do? Hmm? Drop the class again? Then how are you gonna graduate? How are you gonna graduate with a bachelor's degree? How are you gonna get a job? What do you think you need to get a job these days? Well, guess what? My uncle is one of the really higher ups of Google. I think I can get a job there. That might be the case, okay? But in general, you need a lot of ability to process and read information on your own in order to get a job. This class is a pretty good test, okay, of where you stand, okay? Doesn't mean that you'll be stuck if you find this class challenging, but you're gonna have to build up your skills, okay, in order to be competitive when you want to get a job. Okay, at the very bottom of everything that I publish, this is kind of universal, okay? You can click on the top link here. It talks about the copyright of the notes here, which essentially says you can do whatever you want as long as you don't take it and try to publish it as if you wrote the whole thing. Okay. The second one, this link over here, allow you to use GitHub and make some changes, suggesting changes and whatnot, which is kind of cool. The third one is kind of cool too, but the last two links are particularly useful because they allow you to copy and paste the actual text of the material here. And why would you want to do that? If you don't understand it, it's not going to help you if you're just going to copy and paste it somewhere, depending on where you paste it to. So what do you think is my suggestion to paste it to? ChatGPT, and then I see people that, but I don't have a subscription to ChatGPT, okay? Do I have to pay $20 a month just for this class? No. What do you have subscription to? Gemini, okay? Every community college student in California has access to Gemini, okay? So what you do is you copy and paste this into Gemini, and then what do? A prompt that reads like, help me pass this class is not gonna work, okay? Instead, you can say, can you give me examples of how to apply this concept? Can you help explain what this section means? Can you give me some examples of how this works? Okay, those are the prompts that you need to kind of jot down, okay, because it will help you, okay? My notes may not be for everybody, but these days, because we have LLMs, large language models, you can rely on a large language model to say, okay, read this for me and summarize, okay? Read this for me and then give me some test questions so I can try to see if I'm getting a good understanding of the material. So use Gemini in that sense to help you understand the material. Last semester, I have people who essentially just copy and paste the homework assignment description into Gemini, and it generated some programs that would not assemble. Or they won't, in other words, it just doesn't compile. And what kind of score do you think I gave those people? Yep, that's according to the syllabus. Okay, so keep that in mind. All right, so getting back to what I really wanted to do earlier, which is to give you the lab for today. There are two things you need to do. One portion you do at the lab, well, actually both you have to do at the lab, but they would appear to be different things. So this is your lab. Okay, so I'm gonna click on each one and set it up for you. So because I kind of don't kind of delay the starting point, I'll give you guys all that time back. Alrighty. All right, so I'm gonna show the answer at 8:30 p.m. Okay, there we go. And we scroll down here. So you need to write this down. This is the access code to the lab. It is Logisim, all lowercase. Logisim, all lowercase. And I'm still recording, by the way. And there's an IP filter, which means for people who want to go like, I really want to go home and do this lab when I'm home and I can be munching on stuff at the same time. No, once you leave the campus, your IP address will change and they won't let you in. Okay, so this means you have to do it at the lab. This is what in-person means when you look up the schedule. Okay, in-person means in person. Alrighty. So I'm gonna make the due date or the time to be 8:25 p.m. of today. Oh, okay. Doesn't like that. What is today's date? January 20th. Yep, there we go. So we'll make it 8:29 p.m. Okay, just 1 minute before the key is released. Same thing over here. 8:29 p.m. I don't think you will need all that time, but just in case, save and publish. But wait, there's more. At the end of this lab, you'll be creating a Logisim circuit, kind of like the one that I made. So what you need to do is to turn that one in so that I can grade it. So that's what the second companion to the lab is for. It is for you to turn in the file. So, and same due date. Okay, we'll make this January 20th, 8:29 p.m. Okay, just one more thing before I let you guys go. Okay, there we go. All right, so when you look at this part here, there's a lot of instruction. There's a little test circuit that you can use to test the circuit to make sure that whatever circuit you made is going to work. That is optional, okay? It's just one more step so that you can turn in something knowing that you're gonna get full points, okay? But you don't have to do it that way because to do it that way, you have to know your command line interface really well. And I know not everybody knows how to use the command line, so you can kind of not do that part if you don't want to. All right, save and publish. Okay, so now by the time we get to the lab, there are still a few things. The lab technician will want you to register first. Okay, but since this class only has like 20 something people, it's not going to take a long time. So you have to line up, and go like, okay, I need to register to use the lab. And then after that, if you use your own laptop computer, you don't need to do that. Okay, so do we have any questions before I let you go? Yes?
Yes, so about the
Huh?
I have two of those that won't connect to the internet here. I'm taking it to IT. They told me they don't support Linux, all nine yards.
Oh, I know how to do it.
You do?
Yes.
How? I've tried every combination of everything.
For Wi-Fi?
Yes.
Yeah, I know how to do it. I'll help you in the lab. Okay. All right, so we are good to go. So let's go back to the STEM building, go to STEM 301 so we can get started with the lab. And I'll help you with making that connection.